Alright, welcome to Unit 3. In Unit 1 we talked about how everything on Earth is actually moving around on these giant plates of lithosphere and crust and being fueled by convection currents. In Unit 2 we looked at some of the results and effects of that movement, specifically earthquakes, volcanoes, and mountain forming. And now, here in Unit 3, we're going to look at what makes up those big chunks of lithosphere and what makes up the rock that those chunks are made up out of. We're going to start with the small tiny things that make up the rocks, which are called minerals. So to start off, a mineral is a substance that meets four criteria, four characteristics. Sometimes it's considered 5 characteristics, but a couple of them get combined. First of all, it needs to be inorganic, so something that is not from or of a living organism. All right, organic things contain the atom carbon as their base structure. There can be some inorganic things with carbon in it, but most carbon compounds are considered organic. It also must be naturally occurring, must occur out in nature, something that we can find, not something we can just make in the lab. So we have to be able to go out in nature and find it. It has to be a crystalline solid, and this is the one that usually gets split into 2. It's got to have a defined crystal internal structure, this orderly internal structure. That would be a crystal. And it also needs to be solid. It can't be liquid, it can't be gas, can't be a plasma, it's got to be a solid. And it has to have a consistent chemical composition. So if it meets all 5 of these criteria, it's a mineral. So let's take a look at a couple of different things. First off, we have coal. Well, we know we use coal. We can dig it out of the ground. It's a solid, so that's good. But first question is it inorganic? And the answer is no. Coal comes from once living things. All right, let's look at an inorganic compound called brass. Brass is inorganic. It's an alloy of copper and iron, but it does not occur in nature. We melted copper and iron in certain ratios, sometimes added a little zinc, melted those in certain ratios, let it solidify. We made a new metal called brass. So, brass, no, it does not occur in nature. All right, how about a rock called obsidian? Obsidian is also known as volcanic glass. We just talked about volcanoes. Well, when the magma and lava from the volcanoes cools super quick out in the air, no crystals get a chance to form, and so you get this dark volcanic glass. It's called obsidian. It is inorganic. If it's coming from a volcano, it's occurring in nature, but again, it's not a crystalline solid. There's no definite crystal structure in there. The next one is basalt. Chemically very similar maybe to obsidian sometimes. Sometimes it's not. Basalt, we've dealt with this rock before. We know it makes up the oceanic crust. It's inorganic. If it's the oceanic crust, it's in nature. Is it a crystalline solid? Yeah, you can actually break it up, look at it really thin slice under a microscope, see crystals. But it is made up of many different chemicals. 2 pieces of basalt from 2 different oceanic plates or different times of oceanic plate will not have the exact same chemical composition. They will have different numbers of different atoms. So something like fluorite does have that chemical composition. So the 20 most common minerals are called rock-forming minerals, and they are the minerals that form most of Earth's crust, which is where the rocks are. but we don't need to know 20. 10 of these 20 minerals, half of them, are so common that 90% of our crust on Earth are made up of these 10 minerals. And some of them you've probably heard of. There's quartz, orthoclase, and plagioclase, which together make up what are called the feldspars, which is another family of minerals, but they split it into the two subfamilies, the orthoclases and the plagioclases. You've heard feldspars and felsic magma. So quartz, the feldspars, there's muscovite, biotite, calcite, dolomite, halite, which is a fancy name for salt, gypsum, and ferromagnesium, which contains iron, that's the ferro, and magnesium, which is the magnesium part. And we can then reclassify minerals, including these 10, into two main groups. Silicate minerals, which have silicates, which is silicon and oxygen, all right, and non-silicate minerals. And it's all based on their chemical composition. What are they made out of? So the silicate minerals contain both silicon and oxygen. All right, a lot of times with the ion silicate, which is SiO4, so 1 silicon, 4 oxygens, and most of the time the silicate is combined with a calcium or a couple of sodiums or something, contain one or more metals from various spots of the periodic table. All right, common silicate minerals are quartz, which, that's silicon dioxide, SiO2. That's your sand in your glass. The feldspars, and even ferromagnesium, in which case the metals are iron and magnesium. Silicate minerals are about 90% of the continental crust. Like I said, they're felsic. All right, quartz and feldspar alone make up over half the continental crust. So remember, this part of the crust is the continental crust, which we talked about is made up of the rock granite, which is mostly feldspar and quartz, with a little bit of ferromagnesium in there for the dark specks. The non-silicate minerals do not contain silicon and oxygen. That's where the non comes from. They're not silicates, and they make up 4% of the continental crust, and the crust pretty much in general. We break those into 6 major groups, and these groups are the carbonates, halides, native elements, oxides, sulfates, and sulfides. And Chaucin is an easy way to remember it, and this we'll see on the next slide. So the C stands for carbonates, and they have carbon and oxygen. The halides have a halogen, which is that family that includes fluorine, chlorine, bromine, and iodine. All right, oxides, well, they contain oxygen. Sulfates contain sulfate, which is a ion ending in SO4. Sulfides contain sulfur without the oxygen. So sulfate is sulfur plus oxygen. That should be a U. And then En kind of stands for native elements, and this is pretty much any solid from the periodic table of elements. Alright, so big whoop. There's all of these different minerals out there. And there are people out there that go and study the minerals. So we call these peoples mineralogists. Alright, they examine, analyze, classify minerals, always looking for new one. And the reason they can do that is each mineral has specific properties. Alright, and those properties come from their constant chemical composition. An entire mineral is all one substance. And some of these properties come from the crystal structure. Alright, so we can just do simple tests by looking at the minerals or by testing them with fairly common chemicals to identify a lot of these minerals. Pretty simple means. The easiest thing to observe is color. And color is very unreliable. It is not the most reliable of properties. And because we can affect color through weathering, through erosion, and also certain minerals tend to look the same color. Fool's gold, which is pyrite, appears to look the same. It looks like real gold. However, it's different, and fool's gold is not really worth that much. Pyrite can be quite common compared to regular gold. So if we take a mineral and do what we call a streak test, which is pretty much rub it on a streak plate, we get to see the mineral in its powdered form, and streak is more reliable. Fool's gold has a brown to black streak. Real gold has a streak that looks gold. Another really easily observable property is luster. And luster is how it reflects light, or how shiny it is. Alright, we like shiny things. So something with a metallic luster looks very shiny, like a polished metal. Other minerals tend to have non-metallic lusters, and there are different ones. It could look glassy, it could look waxy, pearly, or earthy if it looks kind of dull. Earthy is more of a dull. So shiny is like shiny like a metal. Waxy, pearly will all reflect some light. Earthy is dull. Pretty much we just identify them as metallic luster, which is shiny, nice shiny metal, or a non-metallic luster. The next two have to do with how the mineral breaks. They are called cleavage and fracture. Now, cleavage in geology, it means that the mineral will split along a specific plane. Alright, so it will break off in sheets or form cubes or hexagons or trapezoids. All of these cool little things that you see in this table here, if they break in a regular way along a flat surface, flat breakage, a mineral is said to have cleavage. And if it breaks along 2 or 3 flat surfaces, it has cleavage in 2 or 3 directions. That is different from fracture, which is when a mineral breaks along a curved or irregular surface. Alright, so there's splintery or fibrous fractures, splintery and fibrous that look kind of like this. Uneven, jagged fractures, there's conchoidal fractures, which is the tendency to break in like kind of circular shapes. All this is fracture. Fracture is just like breaking, like your bone would break, or like a piece of wood would break. It's not going to break nice and smooth. Nice and smooth is cleavage. Breaking in a way that looks jagged, rough is fracture. Hardness is the next mineral, and this is how hard a mineral is, obviously called hardness. It's really resistance to scratching. All right, or resist. So it does not mean resistance to cleavage or fracture. A mineral can be really hard and still break along a certain plane. Hardness is how easy it can be scratched by various items. There's a scale out there called the Mohs hardness scale. It's been around for quite a while, and it helps us rate minerals based on how hard they are, from 1 to 10. 1 being a really soft mineral like talc, which is made into talcum powder or baby powder, the stuff LeBron puffs up in or throws up into the air before a basketball game. And the hardest mineral, rated at 10, is a diamond. So this has to do with the strength of the bonds between the atoms. It's kind of going a little more in depth than we need to. Pretty much 1 is soft, 10 is the hardest. This is the Mohs hardness scale. As you can see, there are different minerals on there assigned a hardness. Alright. They will also give you some common tests, like talcum powder can be scratched by your fingernail, whereas gypsum will scratch talc, but talc will not scratch gypsum. Diamond scratches everything. And so as you move down up the list, up the hardness, the minerals become harder to scratch. Alright, an average hardness is right around 5 to 6, right where it can start scratching glass and steel. At 5 it can scratch steel. It's scratched by steel and not, or it's scratched by steel and glass, whereas 6 it scratches glass, so it cannot be scratched by glass, but it does not scratch steel. And then 7 easily scratches both glass and steel. Density is another big property that we can use to help determine different minerals. Density is mass over volume. Guess what? Expect another density question somewhere in this unit. And it all depends on how tightly and how closely the minerals are packed. It's the mass divided by volume. How much mass does it have for a given volume? The more mass in a small volume, the higher the density. There are also a couple special properties of minerals that only certain minerals show. One of these is magnetism, the ability to attract a magnet or to have a magnetic field. All right? Some of them are magnetic themselves, some of them are just influenced by magnetic fields. For the most part, non-silicate minerals that contain iron are more likely to be magnetic. And these are those minerals we talked about when we talked about paleomagnetism in Unit 1 that align themselves with Earth's magnetic field. So not all minerals are magnetic, but some of them are. Another big one is radioactivity. All right, they're not going to turn you into a mutant human walking around with like an extra leg or 8 eyes or something. They just have unstable nuclei that will decay over time, and we'll talk more about nuclear decay in a few units from now when we start talking about the dating of rocks, finding out how old they are. All right, we can use something called a Geiger counter to detect the released particles and identify radioactive minerals. All right, Geiger counters have been around for quite a while. We have a really old one in the classroom. So try to remember to ask me to show you the old Geiger counter. And if I even think of it, I'll plug it in beforehand. Maybe even get the tubes warmed up and bring them radioactive mineral near it. The next two are fluorescence and phosphorescence. Fluorescence is the ability to glow under ultraviolet light. Ultraviolet light is kind of like It's not exactly like a black light, but it's similar to a black light. And so some minerals will glow fancy colors under a black light. Others will absorb that ultraviolet light and they will glow after the light is turned off. They will continue to grow. And that's phosphorescence. So phosphorescence is glowing when the light is off. Fluorescence, it needs to be under the light and the light is on. So fluorescence on, phosphorescence off is when it will glow. And the last one is double refraction. It's property of some minerals, especially some types of calcite, and it produces what is known as a double image called double refraction. If you look through it, you might tend to see double. So it's just a fancy little property because of the way the atoms are arranged and the way light bends through the mineral. And that is a quick little info session on minerals in general. We're not going to look too much more in depth on them, as we're going to spend a little more time focusing on rocks and then move on to bigger and better things. So as always, if you have any questions, I hope you wrote them down. If you haven't, write them down now, bring them in, feel free to ask them, and we will see you in your next class. Have a good night.